Next, we will take a look at chair conformation of pyranose. Back in chapter 2, we learned about chair conformation for cyclohexane. Actually, for all the 6-membered rings, we could have the chair conformations. So these are the two structures of D-glucopyranose. Let's draw the chair conformation for them. For the chairs, this is the only form, while you put the oxygen on the upper right corner position. Okay? Why? I will explain just in a minute. So let's draw the beta form first. On carbon 1, we have OH pointing up, right? And then carbon 2, OH down, carbon 3, OH up, carbon 4, OH down, carbon 5, CH2OH up. It's alternating, right? So now we have the beta D-glucopyranose in the chair conformation. Have you noticed something? What are the positions of the substituents? They are all equatorial, right? The biggest group for all these substituents will be the one on carbon 5, the CH2OH. So when you draw the sugar, the chair conformation for sugar molecules, make sure you put that CH2OH, the biggest substituent, on the equatorial position. Okay? So that's why right at the beginning, I told you to draw the chair in this form so that your CH2OH will be on the equatorial position automatically. All right, this is true for D sugar only. All right. Now let's see the alpha form. For the alpha form, the carbon 1 OH is pointing down. So now, other than carbon 1, all the rest of the substituents will be on the equatorial position. But the carbon 1 OH now is on the axial position. Right? So the alpha form, we have one axial OH. Which one do you think will be more stable? Of course, the beta, because beta has all equatorial and alpha has one axial. All right. And in reality, we have 64% of beta and 36% of alpha. The open chain form is less than 0.01%. So at room temperature in solution, the majority of glucose will stay in the beta form, and the rest of the glucose molecule will stay in the alpha form. They do not have the open chain form. All right. Regarding the hemiacetal equilibrium, how do we go from the alpha form to the beta form? We have to go through the open chain. Okay, so the alpha cyclic hemiacetal cyclic form will open up to give the open chain. And when the open chain reform the cyclic form, it may give the beta form. All right, so the alpha and the beta are related to each other through the open chain. And something is very interesting. For their optical rotation, alpha-D-glucopyranose has a positive 112.2 degrees, while the beta form is only positive 18.7 degrees. Well, if you put a pure alpha-D-glucopyranose in solution, the initial optical rotation will be the number shown here, 112.2. But after a while, slowly, the optical rotation will start to decrease. Decrease to what? To a number that's 52.36. How do we get that? I will show you the calculation in a minute. But now I want to introduce this concept, which is called muter rotation. Muter rotation refers to the change in optical rotation resulting from the equilibration of the anomeric forms, which means the alpha and the beta forms are under equilibrium, and because they have different optical rotation, then the optical rotation may change if you put down one form. Okay, so if you use the pure beta form, the initial optical rotation is 18.7, and if you put it in solution, and after a while, the optical rotation will be increased to which number? The one I just told you, 52.36. And that number is the weighted average. Okay, 52.5 degrees. It's the weighted average. To get this number, we take the percentage of each form times its optical rotation, and the sum of those gives the number. So when the solution is under equilibrium, the optical rotation will be a fixed number, 52.5. Okay, that's under equilibrium. All right. Next, we will take a look at some structural variations for sugar molecules. The first one is a deoxy sugar. So the hydrogen circled here, it was an OH. When it's an OH, that's the ribose, right? Now we change the carbon 2OH to an H in D-ribose. Then we have a 2-deoxy D-ribose. And the 2-deoxy D-ribose is one of the components for DNA. And the DNA is the abbreviation of deoxyribonucleic acid. So now you know the difference between RNA and DNA. It's just one H to replace the OH on carbon 2 in ribose. All right. The next variation is the amino sugar. So the amino group here circled replaces an OH group here. And this is the alpha D glucosamine. I'm sure you've heard this term before, glucosamine, right? It's one of the supplement for people taking it that will be good for your bones, for your mainly for elderly people. Another structure here, we have an acetyl group attached to the amino group. So that's the N-acetyl alpha D glucosamine. Okay, so that's some variation from glucose. And lastly, phosphate esters. We can have phosphoric acid to form an ester linkage with any of the OH groups in a sugar molecule. For example, here the phosphate group is attached to carbon 1. So this structure is alpha D glucose 1-phosphate. And if we have the phosphate attached to a different OH group, like in this second example, that's alpha D glucose 6-phosphate. And these phosphate esters play important roles in the metabolism of carbohydrates.